Hello everybody, and welcome to page 60 on the workbook, and we are at the start of a brand new chapter, chapter 7. Let's just say a couple of words about this topic. So chapter 7 is about differential equations, which is going to be a new topic for most of you. And the nice thing here is that whether you're studying to be an engineer or a physicist or a chemist or a biologist or a mathematician, differential equations are going to come up for you somewhere. This is just a very widely applied concept that comes up all over the place in the sciences and in mathematics. Okay, and I think the best way to illustrate this is just to start with an example to see what differential equations are all about here. So let's take a minute just to read the physical situation that they're giving us here. So they're telling us that an object is taken out of an oven and placed in a room where the temperature is 75 degrees Fahrenheit, and we're going to let T of t represent the temperature of the object after t minutes. Okay, this is a little confusing because we've got two t's in the problem. Capital T represents temperature and little t represents time. Okay, well, this type of a situation can be modeled using what's known as a differential equation. Okay, and specifically the differential equation is this guy right here. dt dt, okay, equals k times 75 minus t. Okay, now I'd like to talk a little bit about what information that's giving us. What do all of those symbols mean in that equation there? Okay, well, let's go down below to the space here, and what we're going to try to do is to describe the components of that equation that we just boxed in. Okay, and we'll start with the left-hand side of the equation, the dt dt. Okay, how would we describe that verbally? Okay, well, that's a derivative, and a derivative really represents a rate of change. So we could say in words that that's the rate of change of the temperature. We could even think about what its units are. It's going to be degrees Fahrenheit per minute because temperature is measured in degrees Fahrenheit and time is measured in minutes. Okay, so the left-hand side of that equation is about a rate of change. And then if you look at the right-hand side, I'm going to ignore the k for the time being and just look at the 75 minus t. Could we describe that in words? Okay, well, what's special about the 75, first of all? Okay, that's room temperature, if you look up there. And so 75 minus t you could think of as the difference between room temperature and the temperature of the object, which is capital T. Okay, so we'll call this the temperature difference. Between the room and the object that's cooling. Okay, and so given those two descriptions of the pieces of the differential equation, could we write an overall description of the physical law? And what we mean by this is we'd like to put into words what this entire equation is telling us. Okay, so we'll read it left to right. On the left-hand side is the rate of change of the temperature, so we could say the rate at which the object cools, okay, and then is equal to, so we'll just say is, and then what's on the right-hand side? Well, there's a constant times this temperature difference that we talked about below. And the way of writing that or saying that mathematically is to call that k a proportionality constant. So we could say that it's proportional to the temperature difference. Okay, between the room and the cooling object. Okay, I'm curious if maybe somewhere along your mathematical journey you might have heard words to that effect, like that sentence that we just wrote. Okay, there's a name for that physical law that we just wrote down in words. It's called Newton's law of cooling. Okay, it basically tells us that an object is going to cool faster if the temperature change between the room and the object is large. All right, so now we want to go a little bit deeper here and think about what kind of information does this differential equation give us. Okay, so let's clear away a little clutter here, and we'll scroll down and start looking at part B. Okay, so now what they'd like us to do is to give a specific value to that constant of proportionality, the 0.5, and then to use that to actually calculate some derivatives here. All right, so if you look at the table below, they're giving us some temperature values and asking us to calculate dt dt for those values. So let's first do the algebra in the space that's here, starting with maybe the value of 25. Okay, so if we substitute t equals 25 into the formula for this differential equation, we're going to be looking at substituting 25 in there. So let's see, we'll get 0.5 times 75 minus 25. And if you do the arithmetic there, what you discover is that you get out 25. That's the value of the derivative. Okay, and the rest of these numbers, exactly the same calculation. If we take 75 and plug it in there, this time we're going to get 0.5 times 75 minus 75, but that's 0, so we're going to get 0 out of this. Okay, and you get the idea here. So the last two calculations, exactly analogous to what we just did. Okay, this time we actually wind up getting a negative number out of that. Okay, and then finally t equals 175. I'm going to trust that you can do that calculation, and turns out to be negative 50. Okay, now I want to remind you what all of these numbers mean that we're looking at. The first row in our table, these are temperatures. Okay, and in the second row, we're talking about rates of change of temperatures. Okay, now here comes a conceptual question for you. Okay, so when we talk about derivatives, what is a graphical way of thinking about a derivative? A derivative is really a slope of a tangent line, and so we can also think of the numbers in the second row of our table down here as being slopes. And what that gives us a way to do is to kind of visually represent this differential equation that we've been talking about. Okay, this formula right here, by interpreting those numbers as slopes. Okay, so if we scroll down to part B here, we are given what's known as a slope field for the differential equation. That's this picture that we're looking at here. It's a bunch of lines drawn in. Okay, and I want to talk about where those lines came from. Okay, so the slopes basically that we're seeing in that picture correspond to the numbers that we calculated in the table up here. So take this column in our table, for example. The temperature is 125. In our picture, that number would be right here. And notice that if you look at the slopes, all of those slopes are negative. Okay, they're going down left to right. And the slopes would actually match this number here, negative 25. Every slope that you're seeing there in that line is negative 25. A computer has actually generated this picture by taking the formula and just calculating the slope, doing the same calculation that we did in the table. Okay, let's look at one more situation. What if t were 175? Okay, then we'd be sitting up here in our table. Okay, and notice that the slopes are still negative, and the values of those slopes should match the number that we got here. So all of those slopes are negative 50. Okay, and you could go to every row in this table, and you would discover that the slopes of the lines in this diagram that we have here match the numbers that we have in our table up above. Okay, and like I say, computers can generate pictures like this, slope fields. All right, next question is, what does this picture do for us? Okay, what can we do with all of these slopes? Well, let's see. Okay, so if we read a little bit farther in this statement, okay, kind of looking at this paragraph here, second sentence, for each initial condition shown below, draw the corresponding temperature function on the slope field. Okay, well, what do we mean by initial condition? Well, that's something like this statement here, t of 0 equals 200. What does that really mean? Well, think of the 0 as being a value of little t, it's a time, and 200 is a value of temperature. So that initial condition is giving you some information. It's telling you, let's suppose that at time 0, the temperature of our cooling object is 200 degrees Fahrenheit. Where would that point be in our slope field? Okay, well, notice little t is here and capital T is here. So 0, 200 would be this point way up in the upper left-hand corner. Okay, so they asked us to draw the temperature function. How do we do that? Well, the idea is to think of every line in this field as representing a slope. So we're going to start at this point, and we're going to try to draw a curve whose slope matches the slopes of the lines that we're seeing. So think of these little marks as being tangent lines and just trying to follow the slopes as best as you can. You generate a curve that kind of has this sort of a shape to it. Okay, I'm going to label that 1, and you can think of that as the temperature function. Okay, so what we get from the picture is that if we start with a temperature of 200 and we follow those lines, our temperature is going to decrease at first pretty quickly and then a little bit more shallowly because the slopes are getting lesser as we go left to right. Okay, let's do the same thing for the next initial condition. So this is telling us that if we start at a time of 0, we have a temperature of 125. So this time we're starting from up here. And we can use the slope field to get an idea of how the temperature would change again. Okay, and we're going to just try to follow the slopes of these segments again. This time the slopes are not quite as steep. Okay, and so our curve still decreases, but not quite as quickly. Okay, so there's our best approximation of what the temperature function would look like. Okay, t of 0 equals 75. This time we're starting from here. And here's something kind of interesting happens. Notice that the slopes are all 0 along this line, so we get a temperature curve that's constant. Okay, and then finally t of 0 equals 25. We're sitting down here. The slopes are now positive, so our temperature actually increases. Okay, now I want to just say a brief word about one of these situations. Number 3 kind of led to a very interesting curve. We got a temperature curve that's constant, meaning that the temperature doesn't change. It stays at 75. Can you think of a reason why that makes conceptual sense in our problem? Okay, well, remember what was special about 75 is that it was room temperature. So ask yourself, if you took an object and you started at a temperature of 75 degrees, would it cool off? It would stay at the same temperature because the temperature matches room temperature. There's no reason for it to change. So it kind of makes sense that we should get a temperature curve that just stays constant at 75 the whole way. Okay, so there is a brief preview to slope fields, and the rest of this section will be kind of just doing some more examples and getting more familiar with this concept of a slope field that we talked about.